Hello, everybody, and welcome back to Introduction to Logic. It is I, your instructor, Sean Hunter, with the Module 5 video. So, hopefully you are hearing the dulcet tones of Mozart as being played by me. YouTube kept kicking all the music I wanted to use because it'd be nice to have some background music. So I decided that if I cover songs that are in public domain myself on my guitar, they can't possibly kick that back, hopefully. Anyway, Chapter 5, Implication and Equivalence, there are four main topics, right? So first we're going to learn about substitution, which is a process we use to replace parts of schemata with other schemata, right? Then we're going to learn about implication, and equivalence, and we're going to learn the fell swoop shortcut for truth value analysis that'll save us a lot of time. So the substitution stuff, the implication stuff, the equivalence stuff is mostly conceptual. You don't have to learn any new skills, and fell swoop, again, is just an abbreviated sort of truth value analysis to save you a lot of time if you recognize where it will apply. It's very useful. So don't freak out this week. There aren't like a billion rules to learn like last week. It should be pretty relaxed. So let's move on and figure out substitution. Okay, substitution. So I'm probably going to ask you what substitution is, that is, to define it on a test. Eventually we'll learn about a similar procedure known as interchange, and I'll ask you to tell me the difference between those two things. But the main use of studying substitution is so that I can prove things to you kind of quickly and easily, or rather so I can borrow Quine's proofs. A few things I have different proofs for that are probably slightly less formal but shorter. So in logic, or at least one of the main uses of logic, is to demonstrate that certain things follow from other things, so that certain theorems follow from certain axioms. Axioms are just things that we assume. Theorems are just the consequences of those assumptions, right? If that goes over your head, don't worry too much about it now, but this is just an important concept to wrap your brain around to understand the proofs for some of the things going forward. You don't need to know or understand the proofs at any great level of detail. I'm not going to test you on them. It's just, this is a logic class, that being one of the main things that you should do in logic. I figure that I have to give you at least some of the proofs. Okay, so I'm not going to write out the definition because it's kind of long, but I'll project it. So substitution is the process whereby, in a schema, we replace every occurrence of one or more letters with some schema. So we have to substitute uniformly, right? And we have to substitute for all instances of that letter. So to give you a really kind of simple example of substitution, let's consider the schema P or Q, right? So if we wanted to substitute for P, I'm just making this symbol up. This doesn't really mean anything. It's just a way of saying what we're going to substitute. Let's say we want to substitute R for P, right? So then this, if we substitute R for P, would go to R or Q, right? Okay, a little more complex example. Let's consider the schema P, and if Q, then R, and all of that, or P. Okay, so here let's substitute R and S for P. So if we sub P, therefore RS, right, that would give us RS and Q, therefore R, or rs, right? So again, we have to substitute every occurrence of p, right? So we have to put the rs in everywhere where p occurs. And we have to substitute the same thing in for p every time that we substitute, right? Just one more example. Again, it's pretty easy. So I don't know, let's PQRS or T, if and only if P Z W. Let's do our dots. Again, technically you could get away with just single dots here. I just think it looks prettier. And if you paid attention to the supplementary video on dot notation, you should understand that it doesn't actually make a difference. So PQRS or T, if and only if P, N, Z, and W. So let's substitute in for P. Let's do A or B. Right, and sometimes this is going to change the dot structure of the schema when we do this. You'll see what I mean. So here, we would get A or B and QRS or T. Oh wait, actually, this needs to be, I'll fix it later. If and only if A or B dot Z W. Okay. I think that's unambiguous. Is that ambiguous? Yeah, it is. Okay. So, right, so here we substituted A or B in for P. So everywhere we have P, so here and here, we replaced it with an A or B, right? So we substituted correctly. And yeah, that's pretty much, if I ask you to do it, you'll be like, oh, that's really easy. So I'm not, generally speaking, going to ask you to do it. So there are two things you need to know about substitution. There are two like fun facts about substitution. The first one is that substitution preserves validity. So to illustrate this, let's consider a schema that we know to be valid, the alternation P or not P. And so let's, for that, substitute A and B in for P. So P goes to AB. So how we would substitute this with a negation sign is this goes to A and B or not A and B. And it's very important that you do it like this, where you negate the whole group, right? This is not the same thing as not A and not B. And next week you'll understand why they aren't the same, but they have a different, they're not logically equivalent. Okay, so we know that the original schema P or not P is valid because, I mean, it has to be true, right? If you did any of the exercises last week, you can figure that out really quickly for yourself with truth value analysis. So we know our original schema was valid, right? So let's see whether or not our substituted schema is valid as well. We're going to do that with a truth value analysis. So just starting with A. Then right, so I'm gonna do these a little bit slow or faster than I've been doing them in other videos. So that gives us B or not B, which is obviously going to be true, right? And so this gives us false or not false. Oh, whoa. Which gives us not false, which gives us true. And you shouldn't trust that kind of one example is enough to prove to you that substitution preserves validity. I'm not going to bother proving to you that substitution preserves validity. You should trust me because you should trust me on authority, as I'm the person teaching this class, and I trusted Quine on authority, and he's a famous logician, so I promise you it does. So the second thing that you need to know, substitution preserves validity, very, 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 very important. Wait, there are three things you need to know, sorry. The second thing you need to know is that substitution preserves inconsistency. Substitution preserves inconsistency. So if we substitute in a schema that's inconsistent, if we substitute anything else in according to the rules of substitution, so we replace every letter, we keep track of negation signs, right? We replace every letter with the same thing, right? We will get, and if this original schema is inconsistent, the resulting schema will as well. So again, we have the schema P and not P, right? We know that's inconsistent. Again, if you don't trust me on that, do a truth value analysis. I promise you it is. So again, let's make, for P, we'll substitute in A and B again. So then we get, and we're gonna A and B and not A and B, right? Actually, this is one of the few instances in which I think dot notation is actually ugly. So if you really wanted to do this for something like this, I don't think I'd care. But anyway, the truth value analysis goes like so. So true B and not true B. Dropping true as components of our conjunctions. We get B and not B. And again, that's going to be false, right? So then we get false B and not false B, right? You could actually, I would be okay on a test if you just went to false there, right? Because you see, if you been paying attention, you'll see that the false is part of this conjunction is going to falsify the whole thing. But if we wanted to do it the long way, just to illustrate, it would go false and not false, which goes to false and true, which goes to false. Okay, so substitution preserves inconsistency. Cool, right? The third thing that you need to know is that it doesn't preserve anything else. So it doesn't preserve consistency. So the simplest example that we looked at of a consistent schema was something like P. And if we substitute, it should be pretty clear why it doesn't preserve consistency, actually. If you've been paying attention and you're clever, you should already have a gist of how this is going to work. So we could substitute something in for P, like let's make P go to A or not A, right? So A or not A, right? So the truth value analysis for P, by the way, is just there. That's all we can do with it. So if we substitute in for P A or not A, we just get A or not A. And the truth value analysis for that will show it'll be valid, right? So true or false, false or true, 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 right? But what if we substituted in an inconsistent schema for P? So we set P to A and not A, right? So A and not A, true, false, false, true, false, false. Right, so if a schema is consistent, there's something that you'll be able to substitute in that might make it valid. There's something that you'll be able to substitute in that might make it inconsistent. Substitution preserves validity and inconsistency, but not consistency, right? And that's really all you need to know about substitution right now. I will be referring back to the substitution preserves validity thing for proofs of different laws, because it makes them, that little fact makes them way shorter and easier. Okay, moving on to implication. Okay, so if you remember the beginning of the class, I said that logic, most of what we'd be doing in logic is testing schemata for various properties and testing to see if certain relations between different schemata obtain. So validity, consistency, and inconsistency are properties of a schemata. And they're the only properties that we really care about in this class. And there are two relations that we care about, implication and equivalence, right? So I'm going to explain what implication is, and I'm going to explain how we test for it. And then in the next section, I'm going to give you a shortcut method of testing for it using your truth tables that you already know and love. So I'm going to give you two different definitions of implication. They're the same, or they're equivalent, but yeah. So most officially, implication means one schema implies another. And this is quoting from our Lord and Master Quine. One schema implies another if there is no way of interpreting the letters as to make the first schema true schema and the second schema false. Right, and so remember, all of our letters stand in for statements. So when we talk about interpreting a letter here, all that we mean is interpreting it as either true or false in the manner of our truth value analysis, right? So it would be really nice if we had a logical operator that came out true in every case except the case where the first part's true and the second part's false, right? And fortunately for us, we do, right? So remember the conditional. Well, what's our truth table like for the conditional? You should all know this by now, but just to redo it. Oops, I need one more thingy. Okay. So, true, true, false, false, true, false, true, false. So the conditional is true in every case except that where the antecedent, the first part's true, and the consequent, the second part's false. So, another way of defining implication is that implication, I had to chant this when I learned the class, is validity of the conditional. Right? So all that means is that if we have some schema, let's just call it schema 1, doesn't really matter what schema it is, and we connect it to another schema, schema 2, with a conditional, if in our truth value analysis it always ends up true, then we know that schema 1 implies schema 2, right? So no new techniques here. What you do if you want to test for implication, you'll be asked sometimes whether or not one schema implies another schema, right? And what you do is you put the first schema in the antecedent place of a conditional, you put the second schema in the consequent place of a conditional, and you do a truth value analysis. So here's a really simple example. So suppose I asked you on a learning practice or a test, right? Does not P imply if P then Q, right? So how would you test for this? Well, we know implication is validity of the conditional. So antecedent of our conditional, again, I'm using more dots than are strictly necessary, as you will see me do all the time. Consequent place of the conditional, right? And we just set it up. We have it set up for truth value analysis. So false, therefore false, therefore Q. That's true, right? Because this whole thing is a conditional. This is the antecedent of that. Conditional with a false antecedent is always true, right? For the right side, we get true. Oh, actually, wait. That should be a true there. Doesn't matter that I made that mistake, but I did make a mistake. Beauty of logic is sometimes you can make a mistake and it doesn't actually make a difference. Very rarely, if you just pick a different number in math, will you end up with a correct solution. Okay, so that's false, therefore Q, right? So we drop true as the antecedent of a conditional, so that goes to false, therefore Q, right? And that's true. Wow, what do you know? It's the first schema does imply the second, right? So that's really all that you, practically speaking, have to know about implication, is that what it means is that there is no interpretation of the letters that makes the first schema true and the second schema false. That means that implication is validity of the conditional, right? So if we want to test whether or not one schema implies another, we connect the first schema to the second schema with a conditional. The order matters, by the way. So if I ask you if like schema A implies schema B, you have to put A in the antecedent place of the conditional. And this is just a really simple example of what that looks like. And yeah, nothing too complicated. You already know how to do truth value analysis. You know what conditionals are. Nothing fancy. So in the next section, I'm going to explain a shortcut test that will make it easier to test for implication. So we won't have to do a full truth table. Yeah. So anyway, on to fell swoop. Okay, fell swoop. So all this is a shortcut. It's a shortcut for doing truth value analysis on a certain subset of schemata. It only applies to conditionals. So in order to apply fell swoop, the schema that we're testing must meet, it must meet at least one, as in it can meet both, and that's perfectly fine. At least one of the following conditions. So the first condition under which we can use fell swoop is that the antecedent of our conditional can only be made true by one unique assignment of truth values. The second condition under which, or the second requirement that we have to meet at least one of in order to apply fell swoop, is that the consequent of our conditional can only be made false by one unique assignment of truth values. Right. This isn't as confusing as it sounds. So let's consider the schema P and Q. Therefore, I guess I don't really need that. Yeah, I'll put it there just for readability. Q or R. Therefore, S. Okay. So, actually, to illustrate, it'll be better if that's therefore P. Okay. So, let's remember our two conditions are if the antecedent can only be made true by one unique assignment of truth values, and that the consequent can only be made false by one unique assignment of truth values. So because the antecedent of our conditional is a conjunction, right? And because if we remember our truth table for conjunction, 3, 4, right, our truth table for conjunction, right, only comes out true when both of them are true. So there's only, if we have a conjunction of any number of letters, or negated letters, but they have to be single negated letters, right? If we have a conjunction that consists only of single letters or negated single letters, then we know that there's only one unique assignment of truth values that's going to make the whole thing true. Right. In the simplest case where nothing's negated, it's just the assignment where all of the conjuncts are true. Right. So instead of doing a full truth value analysis, what we do is we assign true to P and true to Q, because that's what we have to do to make the that's what we have to do to make the antecedent of this conditional come out true, right? So, and then in the rest of the schema, we replace P and Q with true as well. So that'd be true or R, therefore true, right? And so if we're only testing for implication, if that's all we want to know, then we can just reduce this right here according to our rules, instead of having to do the whole thing, you know, do the branches initially, right? And so I guess if I do it pretty worked out, it would be, so drop true as component of conjunction. You could take shortcuts, by the way. I'm doing this kind of the tedious way, but if you've been paying attention, you can probably tell that that you don't need to show every single step, right? So we drop true as the antecedent of a conditional, or R, therefore true, right? Then we reduce a alternation with the true component to true, so true, therefore true, which I promise you is true, right? So it would have taken a lot more time to have done this the long way. Yeah, and so that's how fell swoop works. If we have a schema that meets the first condition, the antecedent can only be made true by one unique assignment of truth values, right? And just to be clear, the assignment of truth values that makes this antecedent true is if we assign true to both P and Q. So the second condition is that the consequent can only be made false by a certain number, or by one unique assignment of truth values. So let's consider the conditional. I'm going to ignore the fact that for this example, the antecedent can only be made true by one unique assignment of truth values. I'm less interested in that. This just for illustrative purposes. P or Q or R, right? So here, if we look at the consequent, the alternation P or Q or R, right? Well, let's look at our truth table for alternation real quick. So Q, P, or Q. Okay, right, so true, true, false, false, true, false, true, false. So true, 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 false. Well, looky there. There's only one way in which we can make an alternation false, right? An alternation is false only if all of its components are false. So for our little schema up here, right, we recognize that it meets the second condition for fell swoop, namely that there's only one unique assignment of truth values that makes the consequent come out false. And that's if we make, if we write out the assignment like this, we get if P is false, and if Q is false, and if R is false, right? That's the only way to make the right side of our conditional false. So we put in false, right, then false or false. And if you've been paying attention to your truth values or your truth tables, and you've been practicing your truth value analysis, you'll see that this is going to come out true, right? So the P does, in fact, imply this alternation, right? So a lot of the time, the examples that I'm going to give you, like for the first condition, you're going to know that that applies because the antecedent is a conjunction of single letters or negated single letters, right? The second condition is if the consequent is an alternation, right? So most of the time you are going to, run into two schemata that you want to test their implication, where if the first one, that you're testing to see whether it implies the second one, if that's a conjunction then of single letters and negated single letters, that you'll be able to do this. Similarly, if the right hand side, the consequent of your conditional is an alternation, right? Then you'll be able to apply this test. There are other ways in which you can construct a schema that this test will apply to. So what happened? Okay. Little glitch there. So like I was saying, there are other schemata that this applies to, right? So if there's only one way to make the consequent false, though it might not look like it, and though you might not recognize it at first, there's actually only one way to make this consequent false. And the only way to make this consequent false is to, is if it's true, therefore, false. Yeah. And I mean, just to show you that this actually is a way to make the consequent false, right? So we drop true as the antecedent of a conditional. Then we drop true as the antecedent of a conditional. Right. Then we drop, or well, then this is false. Actually, that's the only case in which a conditional comes out false is if the antecedent is true and the consequent's false, right? I'm not going to prove to you that's the only way to make it false, but I bet if you're really smart, study real hard, you can figure it out. So if we wanted to kind of plug this whole thing in accordance with that, we'd get true, true, false, right? And it's going to make this whole thing come out true because that's the antecedent of the whole conditional is a negation, right? This is just to show you that how do I say this? That you can apply this in cases other than where the antecedent's a conjunction of single letters and negated single letters, or the consequence and alternation of single letters and negated single letters. I'm not going to expect you to recognize stuff like this. I mean, like I do, but I've been doing this a lot longer than you. Let's look at one more example of fell swoop just to show you what it looks like with negated single letters. So let's check out the schema. Not P, Q, R. Let's see if that implies the second schema. P, therefore R. Right. So again, like there is only one way to make a conditional false. So we could start with the right side, but I'm going to start with the left side. So there's only one way to make this whole thing true. And the way to do that is if we make P false, Q true, and R true. Because if we plug in those values, we get true, 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 for false. And this we have to pay attention to, right? So we made P false here. So that makes it true here because that's not P. We have a negation sign. But here we have to remember that P is false, right? And then false, therefore true. Oops, sorry. Mixing colors. False, therefore true. Okay, so, we this is going to go to true, obviously, and then false, therefore true, and then the right side's going to go to true, right? Because a conditional with a false antecedent, such as this one, always comes out true, and so then we have true, therefore true, and we know that that's going to be true. So once again, this does imply this. Okay, that's really all there is to fell swoop. It's a shortcut. You don't have to take it if you don't want to, but I think that some of the examples here should show you that it would take a really long time to do a truth value analysis and something like that. It would take a pretty long time to do a truth value analysis even on the simpler examples like that or like that. It's always going to save you some time to use fell swoop if you can. So I'd encourage you to use it if you can. You're going to have to do it on the quizzes. But if on a test you can't remember the conditions or it confused you or whatever, you can always do it the long way. You just might take 5 times as long to do it. So moving on to the last section of this chapter, implication or equivalence. Okay, the second important relation between schemata that we'll be testing for in logic is equivalence. First, I'll give you the formal-ish definition, and then I'll give you the more practical definition, just as with implication above. So two schemata are equivalent if, and I'm quoting Quine here, they agree with each other in point of truth value under every interpretation of the letters. Right. So, and once again, you might be like, wouldn't it be nice if we had a logical connective that represented equivalence, right? Quine has a way of saying things a little fancier than he needs to. So all that this means, they agree with each other in point of truth value under every interpretation of the letters. That means that if they always have the same truth value, or as Quine notes, if they agree case by case under truth value analysis. And so the second way in which we will be defining equivalence is validity of the biconditional. And so once again, this means that if we have some schema, let's call it schema 1, right? And we want to know whether it's equivalent to another schema, let's call it S2 for schema 2, right? What we do is we connect schema 1 colors with schema 2 using a biconditional arrow. Actually, I'll make that a different color. Right. S2, and then we do a truth value analysis, and if it comes out valid, so if it always comes out true, right, then we know that they're equivalent. If you understood everything above about implication, this should be like ridiculously straightforward. So here let's just look at one or two really quick examples, because again, it's basically the same thing that you were doing above. Fredo. Okay, so let's see if the schema not P or Q is equivalent to the schema if P, then Q. Okay, so what we do here is just do a truth value analysis. So false or Q, if and only if. True, if true, then Q. Right? And here on this side, we get true or Q, if and only if. If false, then Q. Okay, left side first. So first thing we do is we drop false as a component of alternation. So we get Q, Freedy. Right, so we get Q, if and only if true, then Q, right? Then we drop true as the antecedent of a conditional, so we get Q, if and only if Q, right? And oh, wouldn't you know, that's always going to come out true. So the right side, first we reduce an alternation with a true component to true, so we get, so let me draw my thing, true, if and only if, false, therefore Q, right? The second thing we do is we reduce a conditional with a false antecedent to true, so we get true, if and only if true, right? True. So those two are equivalent. I'm not going to do many more I'm not going to do any more examples of this, actually. It's pretty straightforward. You already know how to do truth value analysis, right? So if I ask you, is this schema equivalent to this other schema? What you do is you connect them with a biconditional, right? And then you do your truth value analysis. And that is all there really is to equivalence. And so this is really all there is in the official part of this chapter, right? So in the rest of this video, I'm just going to, in a very short section, go over the proofs for some of the laws concerning implication. I'm not going to go through all of them. They're all in the book, if you're curious. My book and Quine's book, I guess. So yeah, if you don't have any interest in that, it's not the sort of thing you need to know. You won't be tested on it. But if you find this stuff interesting, you might want to get a grasp on it. Anyway. Okay. Welcome to, I guess, an optional section of this module. I'm just going to go through, how many are there? I'm going to go through the first 4 laws concerning implication that are on page 41 of the book and just go over the proofs of them real quick. And again, this isn't the sort of thing that you have to know, strictly speaking, for a test. I mean, it'll help you understand the material in the course, but I'm not going to test you on it. But again, this is sort of like real proving. Logic's less about sitting there and doing truth value analyses than it is about proving interesting properties or interesting facts about the relations between schemata. So the first law, and it's a simple one, of validity is any schema implies itself. Right, and so how I'm going to convince you that this is true with a proof, quick one, right? Well, let's consider the schema if P then P, right? Let's do our truth value analysis. So it's a short one. Okay, so that's valid, right? If P then P, it comes out true in every case, so it's valid. Now, if you remember that substitution, where'd it go? Substitution preserves validity, right? So if we have a valid schema, such as, sorry for the scrolling. Okay, if we have a valid schema, like if P then P, we can substitute any schema in for P and it'll preserve validity, right? And because implication is validity of the conditional, we know that any schema is going to imply itself. That should be sufficient for you to be convinced, which is really all that a proof is, by the way. Some people tend to think of proofs as sort of mystical, magical things, but all it really means to prove something in math or logic is to give an explanation that is absolutely convincing. Okay, so the second law of implication is that if one schema implies the second, schema implies a second, and a second implies a third, and the second implies a third. Then the first implies the third. Right, so I'm going to do this. It's the same sort of proof, right? So we find the simplest form that we can represent this in our language, and that we're going to show that that's valid, and then we're going to show, or then we're going to use the fact that substitution preserves validity and that implication is validity of the conditional to just kind of make it work for everything. So the simplest case that we can get of this is, well, if one schema implies the second, so if P then Q, and, right, if the second implies the third, so if Q then R, then the first implies the third. So if P, then R, right? I am going to, so there's only one way to make the consequent here false, and therefore fell swoop applies. Again, this is not something I'm expecting you to recognize, but since I do, I'm going to save myself the time. So we assign P to true and R to false. So true, therefore Q, and Q, therefore false. It's true, therefore false. Right, so our analysis is going to go, well, first, just going to make that false, right? So true, therefore Q, and Q, therefore false. False, right? And when we do this, there are often a bunch of different steps that we could take at once. So I'm going to drop true as the antecedent of this conditional here. So Q and Q, therefore false. Therefore false. Right. Then if we have false is in the consequent spot of a conditional, we drop it and negate the other side. So we get Q and not Q. Therefore, false, right? And then we do the same thing. Since we have a conditional with false in the consequent spot, we drop it and negate the other side. So we get not Q and not Q, right? And remember, Q and not Q, the conjunction Q and not Q like that is inconsistent. And that means it's always going to be false. And we know from a previous chapter's law concerning validity, the relationship between validity and inconsistency is that the negation of an inconsistent schema is always going to be valid. So I'm just going to reduce it like so. So we've shown that the simplest possible case is valid, right? So substitution preserves validity, right? So we can replace, as long as we do so consistently, right? We can replace P with any schema, Q with any schema, R with any schema, and this will hold. So that's the second law of implication, right? So the third law of implication, and I'm not going to go through all of these. I think I said that. I'm just doing this for fun. I guess I think this is fun. So the third law is that an inconsistent schema implies every schema and is implied by inconsistent ones only. Okay, so just to make this a little easier, I'm going to reproduce the truth table for the conditional. This isn't one of those substitution-y proofs. Okay, true, true, false, false, true, false, true, false. That would be there for Q. Okay, so true, false, true, true. Okay. So remember, an inconsistent schema is always going to come out false, right? So an implication is validity of the conditional. So if we're asking whether an inconsistent schema implies something, what that means is we're asking what a conditional with false in the antecedent spot implies, right? And the answer is everything, right? Because if we look at our truth table, right, look at the two cases where the antecedent is false, well, it's the whole schema always comes out true. So a schema that's always false implies every schema, right? Because implication is just validity of the conditional, right? As to the second part of it, an inconsistent schema is implied by inconsistent ones only. Well, if we're asking what is an inconsistent schema implied by, the question we're asking is, what sorts of schemata will make a true if we make a conditional connecting them with something that's always false will always come out true. And so, so there are two possible cases in our truth table where the consequent can be false, right? Right, two combinations. So, and if we look at this one, if it's at all possible for the antecedent here to come out true, then this whole thing will reduce to false, right? Because the one case in which a conditional is false is where the antecedent is true and the consequence false. So if we want to know what implies an inconsistent schema, the answer has to be something that always comes out false, and that's going to be another inconsistent schema, right? Actually, I'm just going to do the first three. I think that's enough for you to look through the book, and there are only four. The validity one's basically just the inconsistency one, but with validity instead. You'll be able to figure it out. So those are some laws concerning implication. There are a few more concerning equivalence, right? Again, you don't, strictly speaking, need to know these, but they're logical laws, so I feel obligated to mention them and go through some proofs of them to you. And that's it for Module 5. The Module 6 video on translation will be pretty short, so hopefully this wasn't too bad, and hopefully this will be kind of an easy week. See you guys later.